Good morning, everybody. This is the second lecture of Communication System course. Today we will speak about the Fourier representation of the signals and the systems. This is a chapter 2 in the book that we have. I use for the this course. The book is Introduction to Analog and Digital Communication. It's important in communication to read from the book and solve the questions, the exercises in the book, because communication is not depending only on the instructor, but about the developing technologies. So you have to have a basic, a good and solid basics in the communication. Then you go to the introduced technologies to understand it more. Okay, so one of the basics that we have to master in the communication field is the representation of the signal. So I have a signal like here. I have a signal. I can represent it in frequency. I can represent it in time domain. As I said before in the last lecture, Fourier transform is one of the most important and well-known transformation and representation of the signal in both frequency and time domain. So Fourier transform is about these two equations. So I have the signal. If I have a signal g of t, then I can put it in this equation, g of t multiplied by e to the power minus j 2 by ft. This I take the integral from minus infinity to infinity on the t, on the time. Then this will give me the frequency domain. If I just remove this one, the minus here in the exponential, and if I got, for example, the g of f, I can get the time domain. So it's reverse work. It's vice versa. If I have the time domain, I can use the Fourier transform to get the frequency domain. If I have the frequency domain, I can get the time domain. It's vice versa. So the kernel of the Fourier transform is the exponential to the power minus j to 2 by f of ft. Okay, and this is the inverse. We call it inverse Fourier transform. So here, as you see, I use a different notation. You have to understand that the lowercase denoting lowercase of g here, denoting the lowercase denoting the time function, and the uppercase, if I have used an uppercase, this is denoting the frequency function. Okay, so don't mix it up. So this equation can reconstruct the original time domain behavior without losing any loss of information. So there is no loss in the information using this transformation. Okay, now let's see the conditions in this function. The most important condition, this is all of the conditions that we have, but the most important one is that our signal is finite. It's have a finite number of maximum and minimum, So if I have like this the signal, so if I have it like here, so it have a maxima and minimum. This is the maximum, this is one, this point. It have a finite number here, 3 and 2 minimum, for example. So it have in any intervals from this point to this point, from t equal 10, for example, to t here. So this is the finite interval, time interval, and it's absolute integrable. So it is not giving infinity if I take the integration. This is meaning that if I take the integration of the square, So I calculate the energy. This is the equation for the energy. You take the absolute value of your signal to the square, so you take the square of the signal, and you take the integration of this over this signal. This is the energy. If this condition, if you calculate the energy and you find it that it is less than infinity, so this signal we call it energy signal, then Fourier transform is applicable here. For this signal I can apply Fourier transform without any problem. Okay, so because if you remember that Fourier transform is multiplicating the g of t, multiplicating the signal, whatever it is, g of t multiplied by an exponential. So if the it's go to infinity, then I can't see the effect of the Fourier transform. I can't see the results. Okay, now let's see the notations here. There is some notation I have here. F is the Fourier, is the frequency, the normal frequency, but I can see the angular frequency. It's 2 by f. This is the angular frequency. Also, there is some short notes for the transformation itself. G of t, I can use it to frequency domain and return back here. This is another sketch for the frequency domain and time domain using the analytic tool of the Fourier transform. Now this is the short notation. G of f is equal to f Fourier between these brackets g of t. This is like I apply the Fourier transform to get this side, or the other side. This is direct Fourier transform. The inverse, I take this my f to the power minus 1 of g of f to get g of t. So it is reversible. If I have this side, I can get this side. So as I said, it is reversible. Let's see now. Now let's see the continuous spectrum. What is a spectrum? A pulse with infinite energy. We can express it as a continuous sum of exponential function. Okay, of course this frequency in the interval from minus infinity to infinity, so it is limited. So we can express it like this, in a continuous sum infinitesimal components, so it's limited components, so it not go to infinity. So this is the g of t. This is a function of a Fourier transform. Now this signal can be represented by specifying g of t at each instant of time. Okay, so it can be uniquely defined using the representation. And the Fourier transform g of f, we can say it as the complex function is as a complex function of frequency f, which have amplitude and a phase. Why this? Because we can draw the continuous amplitude spectrum in amplitude and the phase. We can draw it, so we can see we can see the signal in time domain. Now we use this notation so we can see it in the frequency domain. Okay, now let's see for a special case. Of course, here they say that g of minus f, it is the same as g of the complex conjugate, and g of minus f in the complex conjugate, if it is like this, so it is the same in the both of sides, and it is like odd signal. So the minus in the theta here, the theta is the theta f, it is phase, and g of f with these notations in these long brackets, this is the amplitude or the absolute value. Now the spectrum of a real signal is the amplitude and the phase. The amplitude normally is even function, so it is symmetric around the vertical axis or the origin, f equals 0. The phase spectrum is odd signal. odd function. We will see later. So it is not symmetric, it's anti-symmetric. So it is around the vertical axis, the origin. Okay, now let's see an example. The example here gives you a function called a rectangular pulse. You have to remember this. So the function here is rectangular. What's mean by rectangular? It is 1 at a specific interval and 0 elsewhere. Okay, so it is 1 from minus 1 over 2 to 1 over 2 and 0 elsewhere. Okay, this is the definition of rectangular function. Now this is the we can say that our function, if we make a standard definition, it have amplitude of a and have the name rect over t over 1 over t small over t capital. Okay, so 1 over 2 minus 1 over 2, it's 1 here, we can make it 1 over t capital. Okay, this is the where it is. So this is the definition. Okay, all of them, these ones. Now the Fourier transform, let's take the Fourier transform. I want to see the I will see it in the frequency domain. So let's take it from minus infinity to infinity at g of t exponential of minus j2 by f of t dt. Okay, now I want to see that however for minus infinity to infinity it is 0 until we have minus 1 over 2, and after 1 over 2 it is 0 also. So from minus t over 2 until t over 2, this is a definition, it's defined. Before and after it's not defined. Okay, so here I can see that it's a, the amplitude, and from minus t over 2 to t over 2 it is defined, and else it's 0 multiplied by anything, it is 0 multiplied by the exponential again. Okay, now this function, if you solve this, you will reach this solution, sine by f of t capital over by ft multiplied from outside by at capital. So this function we name it as another name. Here we say rectangular. We can see that here we can simplify this function, this one, to have another function. We call it sinc function. Okay, so this function, sine of something, sine of gamma, sine of beta, whatever it is, over the same here, over the same value, we call it sinc function. Okay, so this is the sinc function. Now this is what, this is a rectangular pulse, rectangular of amplitude a, and it begin from minus t over 2 until t over 2. Okay, so don't mix it up with 1 over 2 before in the example. So this is converted, this one g of t converted using the Fourier transform to a sinc function. This is, if you draw a sinc function, you will see this. Okay, this is, of course, this is the not this one, this is the amplitude spectrum. It should be drawing like this, and it go to at infinity go to 0. So the sinc function have an important, this is a very important signal in the communication. Let's see why. Now here the delta, we have delta here, this delta, as I said before, by delta, you can say it f of t, it named by, what is the number, it's not important because you can change t capital here. Now here, as you see, delta is independent variable, it can play any role, it can have any number. So the what important here, it's a rectangular t over t, it's reversed, or in the Fourier transform, it is converted to sinc function. Okay, and the sinc function is converted to rectangular. If you take the reverse or inverse Fourier transform IFT, you will reach this value. Okay, now this is the sinc function. This is the value of sinc function. It is have a amplitude that this is the high value, and it go like this until it go to infinity at 0. Okay, so you see here the spectrum only occur after f equal to plus or minus 1 over t. This is 1 over t. This is of course a, so 1 over t, 1 over 2, 1 over t until it's go to infinity. Okay, now let's see another example. Example 2.2. This is from your book. So a truncated decaying exponential pulse. So this is the function here, shown here, this function. We speak about this function. Of course, this is not the original function of exponential. Okay, so it's different. Now, the exponential function that we know all is here. It's this function. This is the exponential function. So what I see here, it is this complex line, this one. So this is not only a decaying exponential function, it's multiplied by something. So let's first define another function. So u of t, it is 1, where is, so let's draw it here. U of t, it is 1 where it is higher than 0, so it is 1, and less than 0 it is 0. Here it is 0, and here it is 1. Okay, at 0 it is minus, it is 1 over 2. Okay, this is a function, we call it unit step function, and we refer it by u of t. Okay, it is 0 before, 1 after 0 to infinity, higher than 0 here, and it is here, it is 1. We usually make it as 1, so it is from 0 to infinity is 1. Okay, but in this book they define it as 1 over 2, 0.5 at 0. Okay, so let's see. Now here we may express our function here by multiplying an exponential minus at multiplied by the u of t. So this is the expression of our signal here at the truncated decaying exponential pulse. Now let's take, for this truncated exponential pulse, let's take the Fourier transform. So it's multiplied from minus infinity to infinity, the j of t, the exponential minus j to by ft dt. This is the Fourier transform. Now our signal, it's 0 before 0. From minus infinity to 0 it is 0, so we make it from 0. Here the author of the book make it from 0 to infinity because it is 0, and u of t he remove it because it's 1. From 0 to infinity it is 1, so nothing will happen here. So only left exponential minus a of t multiplied by exponential minus j2 by f of t. So you can take both of them. You can take a summation of the power, and it's a normal function of taking the very easy integration of the exponential. You take the integration of the 1 over the integration of the power 1 over a plus j2 by f. So the basic function, it's minus a of t. Here it is a plus. Remember this because it's, if you remove the minus you put it here. So the Fourier transform for an decaying exponential pulse, it is like this: 1 over a plus j by of t, or sometimes we remove 2 by f and we make it j omega. Okay, now let's take the other one, this one. As I said before, the only difference, it's minus t here. you take the minus from exponential to and put it in the minus, so the u of t it is in the other side. So here the u of t, it's you just remove it, draw it like this, 0 before, after, because it's you make everything in the minus side. And I'm sorry, if we take again, so it is 1 for here, it is 1 here, it is 1 at b if t is less than 0 and 0 before. This is the definition of u of minus t. And the exponential, it's like this, so it's, if you take it from the other side, it like it like this. So if you multiply both of them, if you multiply 1 by anything, it will give you like this, if you, it will give you the same thing. So here it's this signal what I'm speaking about, okay, from 1 to and go to infinity, at infinity 0. Okay, now this signal, if you take the exponential function, it's from minus infinity to 0, it's okay, after that is 0, and you take the exponential, you take the summation of the exponential, then you take the integration from 0 to infinity, so it is 1 over a minus j2 by f. Now here it is the difference, it's the plus and minus. So if you take minus a of t minus u of t, it is the minus here. You see, this is this difference. Only the difference is the plus or minus using this one. Okay. Now this is the function that's here. This one you take from minus w to w and 1 here, or this is the phase of, or argument of the phase of this signal. Okay, now I will stop here. Next time I will speak about the properties of the Fourier transform. There is 7 or 8 of them. We will speak more about Fourier transform, but at this stage you have to understand what is the Fourier and solve many problems on how to get the frequency domain or the time domain using the Fourier transform. Thank you very much for listening.